So this chapter is chapter 6, and we'll focus on alkyl halides, nucleophilic substitution, and elimination. So there are various classes of alkyl halides. Alkyl halides are halogens that are directly bonded to sp3 carbons. So here's an sp3 carbon, here's your halogen. Vinyl halides, which is a class of alkyl halides, are halogens that are bonded to sp2 carbons of alkenes. So here's your sp2 carbon. And then aryl halides, which are halogens bonded to sp2 carbons on benzene rings, are shown here. So in general, there is a polarity, as you all know. Dipole moments for an alkyl halide go in this direction. Halogens are more electronegative than the carbon, and so there is this overall dipole moment. So the carbon has a partial positive charge, and the carbon can be attacked by a nucleophile, while the halogen is ready to leave when attacked. In terms of nomenclature, they're named as haloalkanes, so you choose the longest carbon chain even if the halogen is not bonded to any of those carbons. Then use the lowest possible numbers for the position. So for example, here's 4, which is a butane, that's the longest chain, and this is on the 2 position, it's 2-chlorobutane. Here's another one, the longest chain here is a heptane, and then this would be a substituent coming off, and it would be 1,2 after the 2-fluoroethyl 4 in front, 2-fluoroethyl heptane. Here are more examples. Again, this is a 9-mer, which is a nonane, and remember you want to order it so that you get the lowest substituent numbers. So here would be 2 and 6. So this would be 6-bromo 2-methylnonane. Here's a cyclohexane, and in this case it would be 1-bromo 3-fluoro, and they're on the same side, right? They're coming out, so it'd be cis-1-bromo 3-fluorocyclohexane. There are some systematic common names. The alkyl groups is a substitute on an alkyl halide, and they're useful for only for the small alkyl groups. So here's, for example, an isobutyl group, and this would be isobutyl bromide. Again, iso is italics. Here it's sec-butyl bromide. Again, this is sec-butyl bromide. Again, this is sec is italicide. And tertiary butyl or tert-butyl bromide. Again, tert is italicized. Again, when you should be very careful when you're doing an exam. When there should be italicized letters in nomenclature, just make sure you underline it or you highlight it saying that these are in italics. Cis was another thing that should be italics from the previous example. So CH2X2 is called methylene halide. CHX3 is a haloform we've talked about in class previously. Bromoforms, etc., chloroforms. CX4 is a carbon tetrahalide, and common halogenated solvents are methylene chloride, chloroform, and carbon tetrachloride. So there's no way out of this, you're just going to have to memorize those names. So methyl halides are halides attached to a methyl group. Then there's primary alkyl halide, which are carbons to which the halogen is bonded is attached to only one other carbon. Secondary halides are carbons to which the halogen is bonded is attached to 2 other carbons. And then tertiary halides are carbons to which halogen is bonded is attached to 3 other carbons. Here are the pictorial examples of what we've talked about: methyl halide, primary, secondary, and tertiary halides. So there are also different types of dihalides. When they're on the same carbon, and you have two of the halides, this is called a geminal dihalide, or in this case, geminal dibromide. When they're next to one another, each carbon bearing a halide, this is called a vicinal dihalide, or in this case, a vicinal dichloride. And here are the definitions that I just discussed. There are uses of alkyl halides in industry as well as household cleaners and anesthetics. Chloroform has been used as a general anesthetic, but it's toxic and carcinogenic. Right here, this molecule is a mixed halide and sold as halothane, and that's also used as anesthetics. Freons as refrigerants and foaming agents. Problem with freons is they can harm the ozone layer, so they've been replaced by low boiling hydrocarbons or carbon dioxide. And then pesticides such as DDT are extremely toxic to insects, so haloalkanes cannot be destroyed by bacteria, so they accumulate in the soil, and they can be toxic to mammals especially. Dipole moments, as you know, the electronegativities of halides are fluorine, then chlorine, then bromine, and then iodine. Bond lengths increase as the size of the halogens increase. So here's the order of the bond lengths, in which the CF bond is the shortest, followed by CCl, followed by CBr, followed by CI, and then the bond dipoles. This is where you get some trickiness that doesn't follow kind of these two orders. Now you have CCl being the greatest dipole, followed by CF, then CBr, and CI. So the molecular dipoles depend on the geometry of the molecule. So if we look at carbon tetrachloride, carbon's in the center, you have these four chlorines, all the dipole moments are coming out, so this cancels out. So it gives a molecular dipole moment of 0. Boiling points. The greater intermolecular forces, the higher the boiling point. So dipole-dipole attractions are not significantly different for different halides. London forces are greater for larger atoms. Greater mass has higher boiling point, and the spherical shape decreases boiling point. So more branching, you will decrease the boiling point. In terms of densities, alkyl fluorides and alkyl chlorides, and then in the case of chlorides, those just with one chlorine atom, are less dense than water. Alkyl chlorides with 2 or more chlorine atoms are denser than water. All alkyl bromides and alkyl iodides are denser than water. So there are different ways that you can prepare alkyl halides. We already know the free radical halogenation discussed in Chapter 4, as well as your classmates' YouTube videos. Chlorination produces a mixture of products. This reaction is not a good lab synthesis, especially in alkenes where all halogens are equivalent. Bromination is selective, so please note that. So if you want to make selective free radical halogenation, you should select for using bromination instead of chlorination or the others. Free radical allylic halogenation. This is when the halogen is placed on a carbon directly attached to the double bond, which is the allylic position. And so if we look at the free radical methods, we've already seen this. Chlorine, this is free radical chlorination, and you're using cyclohexane. So cyclohexane, all the carbons are equivalent. So in the presence of light, you're going to get chlorocyclohexane. Isobutane in the presence of bromine in the presence of light will generate tertiary butyl bromides, preferring the tertiary carbon versus the primary ones. And so again, chlorination is not selective, so you want to utilize bromination. And in terms of selectivity, tertiary carbons are preferred versus secondary versus primary. Allylic bromination is pretty selective. So the allylic positions, for example, of a cyclohexene are shown here. And so in the presence of bromine and light, you generate 80% of the 3-bromocyclohexane. Hexene, sorry. So allylic the reason why you have such a high yield is because allylic radicals are resonance stabilized. Bromination occurs with good yield at the allylic position right here. Your reaction mechanisms. So you've already talked about in chapter 4 free radical reactions. So after generating the radical will react and form a bond with the H. This will then produce a radical right over here. This allylic radical can undergo resonance stabilization. So here are the two resonance structures. They're equivalent. And then when it's ready to form, this radical will react with another bromine from the diatomic bromine, regenerating the radical and generating the allylic bromide. Now again, half arrows are being used because this is again a radical reaction, so you have to be very careful and not use full arrows in such mechanism. And both of these allylic radicals can react with bromine. NBS or N-bromosuccinimide, shown here, in the presence of HBr, reacts with HBr to generate the debrominated molecule with Br2. NBS or N-bromosuccinimide is an allylic brominating agent. It actually keeps the concentration of Br2 low so that it can selectively brominate at the allyl position. So here's a new reagent. So in the NBS, in the presence of light, will react with this alkene. The allylic positions shown here. So here, this carbon is the allylic carbon. Also, this and this and this are equivalent. So you can generate your allylic brominated product. Also, the other possibility is that you can, through resonance resonance stabilization, you can have this being moved up and the bromine coming to here, the tertiary carbon. In terms of reactions with alkyl halide, you can have nucleophilic substitution, which we also discussed before, in which your nucleophile can come in, right, attack the carbon, and then kick off the halogen. So this would generate the product. And then elimination is the other possibility, in which the base will pluck off that hydrogen, form now the double bond, and kick off the halogen. If we look at an SN2 reaction of hydroxide reacting with iodomethane, you have a reaction where we're going to draw out the arrows in this case. You're going to have the electrons from that oxygen, attack that carbon, and then kick off the iodine. And this is an SN2 reaction. What happens in an SN2 reaction, you have this whole thing happen in concert, and you have change of stereochemistry if this was chiral. So you have, but since this isn't, you don't have any change in stereochemistry. So in this case, unlike the free radical reactions, you have a heterolytic cleavage instead of a homolytic cleavage, and your iodine is happy to leave and be as floating in the solution. And so now you've just generated an alcohol in this case. So here's the SN2 mechanism. It's a bimolecular nucleophilic substitution. oops. As you can see, you have the arrows, so the electrons from the oxygen and the hydroxide comes and attacks the central carbon right here, then kicks off the iodide. In that whole process, there's this transition state. Remember, there's a double dagger in the transition state, and it's slightly negatively charged. And you see that here, you're seeing kind of what's happening with the hydroxide coming in and the iodine being kicked out. And then the product is your alcohol with your leaving group. Again, it's a concerted reaction, new bond forming and old bond is breaking at the same time. Reaction is second in order overall. Reaction rate is the K, R, sub R, with the alkyl halide concentration and the nucleophile concentration. This is what we've already discussed in the previous chapters. In terms of an energy diagram, here is energy plotted as a function of reaction coordinates. You're starting off with your two reactants. It undergoes a transition state. Again, a double dagger is shown with an overall negative charge because the hydroxide is negative. And then you have the product. The product is lower in energy. You generate the alcohol and the iodine. And so this SN2 reaction is a one-step reaction, as shown here. And the transition state, of course, is the highest in energy. And if you wanted to figure out what the activation energy is, that would be this right here, right? That's the activation energy. Sorry, with my handwriting, it's not so pretty, but hopefully you guys get it. And then because it's lower in energy, it's an exothermic reaction. So here are uses for SN2 reactions. You can generate, depending on what your reactions are, you can generate a new alkyl halide, alcohols, ethers, right? So alcohols, you have a hydroxide, ethers, you have an OR. You can generate a thiol, right? A thioether, right? If you react it with an amine, you can generate an amine salt. If you react it with an azide, you can generate an azide. Alkyne, you generate an alkyne. Nitrile, you can generate a nitrile. You can also react it with an ester salt to generate an ester, and phosphonium or phosphorus to generate a phosphonium salt. So nucleophilic strength, stronger nucleophiles react faster. Strong bases are strong nucleophiles, but not all strong nucleophiles are basic. So in your table in your chapter 6, table 6.3, here are common nucleophiles listed in decreasing order of nucleophilicity in hydroxylic solvents such as waters and alcohol. Here are your strong nucleophiles, moderate ones, and then weak nucleophiles. So again, my suggestion would be to make flashcards so that you just know which ones are strong ones, and moderate ones, and weak ones. Basicity versus nucleophilicity. Here's an example of basicity in which you have your nucleophile that could, in this case, is basic, so this will then pluck off that hydrogen, kicking off the halogen, generating the new product, and the halide. In nucleophilicity, what happens is you have it attack the carbon. Basic, it just plucks off a proton. Nucleophile attacks the carbon, kicks off the halide to generate a new covalent bond to the carbon and kicking it off. So basicity is defined by, importantly, equilibrium constant for abstracting or plucking off that hydrogen, which is a proton. Nucleophilicity, on the other hand, is defined by the rate of attack on the electrophilic carbon. So how fast this can go, so it's defined by the rates, Kr. So one important thing to note is that steric hindrance or bulkiness hinders nucleophilicity. I'm going to underline that because that's critical. more than it hinders basicity. So if we look at trends in nucleophilicity, a negatively charged nucleophile is stronger than its neutral component. So this will be always, the hydroxyl will be always a stronger nucleophile than the neutral component here. Again, here's your thiol, and here's your amine, or actually, this is your amine, and this is your nucleophilic amine. And nucleophilicity decreases from left to right, so as you go from iodine to bromine to chlorine to fluorine, here's the trend. Selenium, hydride, thiol, hydroxide, here's your trend. Triethylphosphine, triethylamine, here's your trend. So again, you can utilize your periodic table and just know that if you go from left to right, you can have this trend of decreasing nucleophilicity. And as you go down the periodic table, as the size, as you go down the periodic table, it increases as the size and polarizability increase. So again, here's your trend where you have your nucleophilic amine, hydroxide, fluorine, amine versus water, triethylphosphine, this is diethyl, which is a sulfide, so, or diethyl thioether. So so these are trends based on going down the periodic table, increase. Polarizability effect. So if we look at, for example, fluorine, which is a hard, small valence shell, and here's the backside lobe of your carbon here that you're going to be trying to attack, you're going to have little bonding in terms of overlap of this small valence shell with this sp3 orbital back lobe, because the fluorine is small, so there's little bonding in the transition state. Double dagger again, negative charge. However, if you have a soft, large valence cell, such as iodine in comparison to fluorine, now you're going to have more possibilities for overlap. As a result, you'll see bonding, and here is your transition state again. So bigger atoms have soft shells that can start to overlap with the carbon atom from a farther distance. And if we look at solvent effects, protic solvents, for example, with hydrogens that can donate, can solvate the fluorine. As a result, these polar protic solvents reduce the nucleophilicity of the fluorine and then prevent it from attacking the carbon and kicking off the halide. And then if we look at the transition state, the solvent is partially stripped off from the transition state in order for this to happen. So the nucleophilicity in protic solvents increases as the size of the atom increases. Solvent effects. In terms of solvent effects, aprotic solvents, here are some examples of aprotic solvents. These are still polar: acetonitrile, dimethylformamide, and acetone. Polar aprotic solvents do not have acidic protons and therefore cannot hydrogen bond. Some aprotic solvents are acetonitrile, as we showed here, DMF, acetone, and then DMSO. SN2 reactions proceed faster in aprotic solvents because there's no hydrogen bonding. Crown ethers. Crown ethers solvate a cation, so the nucleophilic strength of the anion increases. So for example, here's 18 crown 6. It'll solvate the potassium, allowing for the anion to be nucleophilic. So then the fluoride becomes a good nucleophile of KF because the 18 crown 6 will solvate that cation, allowing for this reaction to occur. So remember, if you want to use fluoride, which is not usually a good nucleophile, with respect to the other halides, you can use 18 crown 6, and here's a polar A protosolvent to help as well. Leaving group ability, the best leaving groups are electron withdrawing to polarize a carbon anion. They're also stable. They're not a strong base once they've left. And then they're polarizable to stabilize the transition state. So as an example, here's your table 6.4, weak bases that are common leaving groups. You have your halides, sulfonates, sulfates, and phosphates shown here as examples. And then neutral molecules, water, alcohols, amines, sulfides, and phosphines. An important thing to note again here is that you don't write SN2 reactions that show hydroxide ions, alkoxide ions, or other strong bases serving as leaving groups. This will likely not happen. And so remember that SN2 competes with elimination, so SN2 will not be likely preferred when these can likely occur, would be possible occurrences as leaving groups, because they won't. The structure of substrates on SN2 reactions, if we look at SN2 reactions in terms of reactivities for substrates, methyl halide is most preferred, followed by primary, secondary, and tertiary. And if you look at the difference between secondary and tertiary, it's really not preferred for tertiary. Tertiary halides do not react via SN2 due to steric hindrance. So we're going to stop here and then continue on with the second half in a bit, in the next part 2.